So, now we know how to calculate the shift factor. So, after calculating the shift factor, how to shift the data. So, as I mentioned earlier, we shift the data only horizontally, only on an x scale and not on a y scale. Now, if you look into this typical example of shifting, see you have a this is dynamic modulus, it is not a complex modulus, we call it as a dynamic modulus. As Professor Murali Krishnan already pointed out, dynamic modulus and a complex modulus were used interchangeably to denote the mod of complex number. So, let us take this as a dynamic modulus value. Now, if you see this dynamic modulus value is captured at different frequency, these are the direct experimental data. So, you have an experimental data here measured at different temperature starting from 10 degrees Celsius to all the way as high as 75 degrees Celsius. So, you have different dynamic modulus data. So, our test temp frequency region here is very limited. So, the one which is red color here is 25 degrees Celsius data. Now, find the equivalent modulus point from a 25 degree Celsius. Now, let us take a case for 15 degrees Celsius. So, this 15 degree Celsius data, knowing the shift factor, we can move in this direction to match the 25 degree Celsius data. So, once you move this, so nicely the pink line and the red line is like it came on the same point, same one single line. So, 15 and 25 degree matched. So, you can likewise match the two pairs of data to a reference temperature, knowing the shift factor value. Shift factor is nothing but the amount of shift we do it horizontally. So, it is just an horizontal shift. So, the modulus value will never change, only the x scale will change. If the x scale changes after shifting, we call it as a reduced frequency. So, it is reduced frequency, not just a frequency, it is reduced frequency. If we generally denote a frequency by omega, reduced frequency we denote it as omega r. See, this reduced frequency is since it is in the logarithmic scale, so it is AT into omega. So, we are shifting it, we are adding it either plus or minus. So, since it is in the logarithmic scale, the reduced frequency can be calculated from this AT into omega. So, now after shifting, you can see that no calculations have been done, it is just shifted either to the left or right, keeping a reference temperature to be 25 degrees Celsius. Now, you can see that there is a discrepancy in few data in this temperature region. If this corresponds to 65 degrees Celsius, this corresponds to 55 degrees Celsius, and this data corresponds to 45 degrees Celsius. So, you can see a discrepancy in the data from the curve, main curve. So, this discrepancy in the data happens if the response of the material is not thermorheologically simple. One condition is, other is if the measurement goes out of non-linear region. So, we measure modulus. This modulus measurement of E value or a dynamic modulus value here, if we represent it by G star, measurement of G star if it goes in the non-linear or any other testing artifacts, but we cannot use these data, we have to remove these data before we do a master curve fitting. So, now the next question is, we have defined what is time temperature superposition principle. Can we apply time temperature superposition principle for all cases? The answer is no. As I said, we can apply the time temperature superposition principle when the material exhibits a thermorheological simple response. So, when the material is thermorheologically simple. What is this thermorheologically simple is, if let me define it in terms of a relaxation modulus or a relaxation time. So, if a material at two different time exhibits the same relaxation process, we can call it as a material to be thermorheologically simple at both the temperature. So, or otherwise there should not be any transition when you move across a different temperature. So, if there is no transition in the range of temperature we are looking for, then we can apply a time temperature superposition principle. Or if you want to describe in terms of internal structural changes in the material, so there should not be any structural changes in the material like crystallizations etc. To happen within the temperature range. If then we can call as a material to be thermorheologically simple. So, we study the response of a material over a wide range of temperature. Within this wide range of temperature, if the material exhibits the same relaxation process, or there is no transition in this regime, transition in the flow behavior or no transition in the internal structures, this transition in the internal structures induce the rheological changes. So, if there is no any transition occurring in this wide range of temperature, we call the material response to be thermorheologically simple. So, let us come back to a bituminous material. Now, is the bituminous material thermorheologically simple? So, for this next question, whether the bituminous material is thermorheologically simple, let us look into a behavior of bitumen over a wide range of temperature. So, right from a glass transition temperature, or we will start well below a glass transition temperature. You know what is glass transition temperature? So, for a glass transition temperature of a bitumen, we will take it as Tg. So, well below the glass transition temperature of a bitumen, the bitumen will behave as a elastic material. Generally, this occurs near 20 degrees Celsius. It is near 20 degree and this value is not fixed. It varies with the binder type, it varies with the aging conditions, many other factors, testing equipment we use and many other factors. So, like let us assume like the Tg is near minus 20 degrees Celsius and the response of a material below Tg will be typically elastic. So, above Tg when you proceed, the response of the material will be viscoelastic. So, as the temperature further increases, there will be a transition from a viscoelastic to a Newtonian temperature. This temperature, this transition may happen near say 100 degrees Celsius. Again it is a near temperature, it is not exact value here. So, this is a viscoelastic range of temperature, below Tg is the elastic range of temperature and above 100, in this case above 100 it is Newtonian. So, you have, as we change the temperature, we increase the temperature from as low as minus 50 to go even up to 160, 170 degrees Celsius, bitumen exhibits three kind of response. At very low temperature it is elastic, at intermediate temperature it is viscoelastic and at very high temperature it is Newtonian behavior. So, now if you have three different response of a bitumen, if you consider as such as a whole, the bitumen is not thermorheologically simple, but you can assume that the material is thermorheologically simple within this region, viscoelastic temperature region, or you can assume that the bitumen is thermorheologically simple in this elastic range or in this Newtonian range, not from one to other. So, in this transition range, bitumen, if you consider over a whole temperature, bitumen is not thermorheologically simple. So, if you just consider only the viscoelastic behavior, we can say assume that the bitumen is thermorheologically simple. Even here you might have learnt already viscoelastic solid like behavior, viscoelastic fluid like behavior. So, as the temperature increases in this viscoelastic range from Tg to high temperature, there will be a transition happening from a viscoelastic solid to fluid like behavior. So, this solid like to fluid like behavior, we have already seen that in a small amplitude oscillatory shearing, that this transition is frequency dependent. So, there are many other factors like the solid to fluid like behavior varies. So, there is no fixed method to identify what is the solid like behavior or a fluid like behavior as of now. And let us not move in detail about whether this solid like behavior and fluid like behavior has to be considered as a transition. So, we will as of now we will take it as viscoelastic material. Bitumen behaves as a viscoelastic material in this temperature range. So, from -20 near -20 to near 100 degree, and we can apply a time temperature superposition principle, and this is the temperature range where all payment engineer is also interested in. So, this is an example where the data oscillatory shear data was shifted using a time temperature superposition principle taken from a Leuscher. So, this compares a master curve after shifted. So, master curve of two samples, one is an asphalt, some asphalt A, we don't, let us not worry about what is that A, another is asphalt A plus 10% wax. So, one plot here gives you the modulus, storage modulus and the loss modulus, the other plot is a phase angle. So, now if you see asphalt, just asphalt exhibits a nice, it has a nice smooth master curve, but with the wax here you can see a discrepancy here or a deviation in the data from a main curve, and if you can very well see it in the phase angle. So, phase angle is very sensitive function. So, we can, if you want to check whether the material is thermorheologically simple or not, you can use a phase angle function. So, you can see a discrepancy in the data at lower frequency. So, lower frequency corresponds to a lower temperature data. So, at high, as the temperature increases from low to high, we know that the wax melts. So, there is, or when you move from high to low temperature, there is a crystallization happening. If in the presence of wax, the material may crystallize, and you can see as the material crystallizes, or there is a change in the internal structure of a material, you can see a discrepancy in the data when you construct a master curve. So, now the next is after conducting an experiment. Now, if we wanted to construct a master curve with our experimentally available data, so before even attempting to construct a master curve, you may want to know whether I can use the entire data in constructing a master curve. So, for that, to check whether you can use the entire data for constructing a master curve, you can use or construct a block diagram, or you can use a Kramachronic relation and check the data consistency in the data and filter your data based on the results and then construct a master curve. So, what is this Blockspace diagram? So, this Blockspace diagram is nothing but the relation between a dynamic modulus and a phase angle. So, this dynamic modulus and a phase angle is obtained from the oscillatory shear testing after conducting a frequency sweep test. So, you have at different temperatures, you can see from 25 to 675 degrees Celsius. So, this is nearing, this is 25 degrees Celsius, and the maximum here is 75 degrees Celsius. The dynamic modulus and the phase angle functions are not an independent functions. So, if it exhibits a smooth trend, we can use that data for the construction of a master curve. So, now here for this case 65 degrees Celsius data and 75 degrees Celsius data do not follow a smooth trend. So, once you remove this 65 and 75 degrees Celsius data, you can see a smooth trend in the dynamic modulus and a phase angle data. This is based on the concept that dynamic modulus and phase angle are not an independent function. We already saw this. So, the next approach for checking the data is you can use a Kramachronic relations. So, this is also widely used for a bitumen and bituminous mixture to check the consistency in the dynamic modulus and the phase angle value. See, we know that complex modulus has two parts. The real part is what we call it as a elastic modulus, and the imaginary part is what we call it as a viscous modulus. So, this elastic modulus and viscous modulus is not an independent function. Kramachronic's equation gives a relation between this elastic modulus or a viscous modulus, or otherwise a dynamic modulus and phase angle. So, the Kramachronic relations is as given in this equation A. Let us not worry about how this equation is derived. Now, if you see this delta value here is phase angle as a function of frequency, depends on the modulus value and the frequency here. So, delta is related to a dynamic modulus using this equations. So, now what you can do is use the dynamic modulus value obtained experimentally, compute a delta value from the experimentally obtained dynamic modulus value, compare this computed delta value with an experimental delta value and check whether there is a consistency in a dynamic modulus and a phase angle recorded. One such an example is given here. So, if you see a x scale, it is an experimental phase angle, and y scale is computed phase angle computed from the dynamic modulus value using a Kramachronic relations, Booge-Thorne relations, which was given here. So, this equation was derived by Booge-Thorne. So, Booge-Thorne equation as given here is used in computing the delta value, and it is plotted here. So, now if you see this comparing a computed phase angle and the experimental phase angle, you can see that at higher temperature, maybe around this is 45 degrees Celsius, there is a discrepancy from the 45 degree line. This line is 45 degree. Along this line, computed value is equal to experimental value. So, if data deviates more from this, it indicates that the Kramachronic relation is not applicable. So, you can see that at 45 degrees Celsius, there are some data where it does not fall into a Kramachronic relations. So, while fitting a master curve, you remove these data from the experimental data and then start fitting the master curve. So, now we know what is time temperature superposition principle, we know how to calculate the shift factor. Once you know how to shift it, amount of shift, now how to do a shifting process or construct a master curve. So, as pointed out earlier, master curve is shifted using a horizontal shifting, only we do a x axis shifting. So, for shifting that we follow a two approach, one is a free shifting, another is a constrained shifting. So, in a free shifting of a data, what we do is we take a successive pair of dynamic modulus value or a relaxation modulus value. So, we take a successive pair of isotherms and make it a smooth curve as given here. So, in this example, again it is a dynamic modulus data as a function of frequency. You have a different temperature data varying from 3 to 40 degrees Celsius. Suppose if we need to shift all the data corresponding to a 3 degree. So, here reference temperature is 3 degrees Celsius. So, now this find out a pairwise, just take first 3 and 10 degrees Celsius, find out amount of shift. Now, next is from 10 to 20 degrees Celsius, what should be the amount of shift. So, find out a pairwise, do a pairwise shifting and find out what is the value of AT based on a pairwise shifting and shift the data. So, this is one method, it is a free, we call this as a free shifting. So, in this free shifting process, we do not assume or give any trend for a final master curve. We just find out what is the shift factor between two pairs of isotherm and then just shift the data. Now, in the constrained shift process, we define a final form of a master curve. It can be a sigmoidal shape or an any shape. MEPTG design uses a sigmoidal shape master curve. So, let us just look into what is sigmoidal shape master curve. Now, again the same kind of a data, dynamic modulus data as a function of frequency, you have it here. Now, we have at a different temperature. If we want to shift the data to a reference temperature of, here it is given as 70 degree Fahrenheit. So, reference to the shift the data to a reference temperature of 70 degree Fahrenheit, you have a low temperature data minus 16 degree F and a 40 degree F and a higher temperature data here. So, now here if you want to shift this data along as marked directions, so what you do is define a first a curve shape and shift the data accordingly. So, sigmoidal equation states this: log of dynamic modulus value is a function of this delta. Delta here is not a phase angle. So, this is the equation as such given in NCHRP. This delta is not a phase angle which we used previously. So, you have a delta, alpha, beta, gamma, these are all some material functions. Now, if you take this delta value is G minimum, as such it is given as E here. So, it is E minimum value here. So, lower frequency asymptote functions, and alpha value is an delta plus alpha value together will be an higher frequency asymptote function. So, now this equation becomes a sigmoidal functions with the minimum value as delta and maximum value as alpha plus delta. This beta and gamma functions describes the slope functions in this range, and TR here is a reduced temperature, here it is reduced frequency. So, now you fix the form of a curve and shift the data to that form, we call it as a constrained shifting. So, if you do a shifting, you can see a sample master curve, we will get it. So, dynamic modulus master curve and a phase angle master curve. So, for a different bitumen, you can see a dynamic modulus varying smoothly. As the frequency increases, there is an increase in the dynamic modulus value. Here again, as the frequency increases, so at high frequency material will become more elastic like. So, we expect the modulus to phase angle to decrease as the frequency increases. So, that is what happening in a bitumen B1 sample, B2 sample and B3 sample. Now, if you take a B4 sample, so you have a range here of a frequency where the expected trend is following. Okay. There is a range here, another where you expect an increase, but you have a rubbery kind of a region here where the frequency phase angle is almost constant or just reducing. So, this is due to a internal structural change that is happening at this frequency, reduced frequency. So, this kind of a rubbery behavior is a material behavior that happens for this particular material. Do not worry about what this material is. So, our focus is not what the material is, our focus is only what kind of a phase angle master curve we may get it. So, this kind of behavior can be captured when you construct a master curve. This is another advantage or an application of a master curve. So, now let us summarize the steps that we use to construct a master curve. So, for constructing this, you have to first identify, you have to do an experiment, frequency sweep test in a frequency mode or relaxation test or a creep and recovery test at different temperatures. So, now you have a different temperature data as a function of frequency or as a function of time. Now, so with if you have a different sets of data, identify a temperature range that can be used to construct a master curve. So, you may have a data from maybe from all the way from 0 degree Celsius to 100 degree Celsius, but we may not be able to use all the set of data. You have to check whether you can use it using either a Blockspace diagram or using a Kramachronic relations. So, filter the database using a Blockspace diagram and a Kramachronic relations. After filtering that, now select the reference temperature and shift all the data to this reference temperature. So, this selection of reference temperature is based on our requirement. If you want to know the response of a bitumen maybe at 35 degrees Celsius, so you select it to be 35. So, it is based on the user requirement and there is no any fixed scale to select the reference temperature. So, after selecting a reference temperature, find out the shift factor for each isotherms. So, for finding out the shift factor, you can either use a WLF equation or you can even use an Arrhenius equations. So, once the shift factor is determined, find the reduced frequency or reduced time in case of a time scale testing using this relations. Once the reduced frequency or reduced time is determined using this reduced value, shift all the modulus value in a horizontal scale, keeping the x scale as reduced frequency or reduced time in case of a time domain testing. So, once you shift all this data, you will get a nice smooth master curve. So, so far we have seen what is time temperature superposition principle and how to use this time temperature superposition principle in constructing the master curve. In the next lecture, we will see what are the different models that is available for to predict the response of bitumen. Thank you.